Hey, Physics 20s. Okay, we're going to go over these review questions. If you want to see these, I put them on my Google Classroom. Print them out, try them out. There's about 74 questions. We're going to have to split this video up into two. You can always just check out the PDF version of this, but if you want an explanation, just go to the question you're looking for, and let's get going. All right. So we've got a baseball here thrown into the air, neglecting air resistance. Very important there. You're going to neglect air resistance. Yeah, so that means the forces, the only force acting on that thing would be gravity at this point. If I'm neglecting air resistance, then anything horizontally, there's no forces. So it says here the vertical acceleration of the baseball after release depends on, so it depends on the mass of the ball? No, like if I neglect air resistance, if I drop two things, like this ball here and this pencil sharpener, and I drop them, they're both going to drop at the same rate. So that's wrong. Let me just cross that off there. Right. All right. The vertical component of the force exerted on the ball by the thrower. This is after it's being released. Most of the time we don't talk about like as he's throwing it up, he's going to apply a force. He is. That's how he gets it to accelerate to the rate it's at. But then after he lets go of it, no, we don't care about that one. All right. Horizontal component, no, because we're talking about vertical anyway. It's all about the gravitational field strength, right? So this is that little g. This is the 9.81 newtons per kilogram down, or the 9.81 meters per second squared down, right? So it's going to be just dependent on that, really. So it's got to be D. I don't know where question 1 went off to. Whatever. The following data collected during observations of motion object. What can be inferred about the motion of this object? Okay, so let's see. We got some numbers here. It's going up 2, 4, 6, 8, and then we look at the other numbers. They're going up by 6 each time. So if I were to sketch this out, so it'd be nice if you kind of remember to identify the types of graphs we might get here, right? So if I have a displacement time graph, position time graph here, and it says here at time 0 I'm at like 20, and then I'm in the next one, then I'm in the next time. I get this nice straight graph. Now if I do my rise and my run over each one, it's going to be like 3 meters per second, right? It's going to be 6 divided by 2, 6 divided by 2, 6 divided by 2. It's going to be the same amount each time. So we're moving at a nice uniform velocity. Okay, we're not accelerating because that means the graph would be curved, right? It makes curved graph, so it can't be accelerating. So we already know that. We just have to determine what the speed is. So remember that the slope of a distance time graph, that is equal to the velocity, which is just equal to change in distance divided by change in time, right? So this is going to be, it doesn't matter which 2 points you take, and as long as it's all constant, then we're moving at a constant velocity. So I could pick like the 20, I can pick from the 20 to the 26, so I can go from the 20 all the way up to the 44. If I do that math, I should get the same answer either way. So say I went up to the 20 to the 44, right? So my final position, 44, minus my initial position, 20, divided by my total time here from 8 seconds to 0 seconds, just 8 seconds there. So I'm doing the calculation in my calculator for some reason. I get 24 divided by 8, which is 3 meters per second. So we're moving at a uniform velocity of 3 meters per second there, so it's got to be B, right? Not a curved graph, right? It's a nice straight line. Truck driver travels west, then east, then west again. What's the average velocity? Okay, so remember there's 2 different kind of questions I could ask here. What's the average speed? And what's the average velocity? So the average velocity, you have to find the total displacement. Now, there are 2 ways to calculate displacement here. I was just talking with the Science 10 student here earlier. To find displacement, I can do either one of 2 ways. I could do my final position minus my initial position, as long as I know their positions. But I don't know their position, right? Or, Or I can do, to find the displacement, I could just add all the displacements together. Displacement plus the displacement plus whatever other displacements we have, right? So that's the way I'm going to want to do in this question, right? So it's either one or the other, right? So since I don't know their final initial positions, I could say their initial 0, but I don't know what the final is. I'm just going to add all the displacements together, right? And they got all these displacements, or thing is I got to find the displacements. Well, I do. I know all the displacements, right? So when I'm doing this, we have to remember these are all vector quantities. So I got all these west, I got this east, and then I think I got another west over here. Yep, another west, right? So I got all these displacements I got to worry about. So when I'm adding displacements together, we still, and same thing with position, we have to worry about our sign convention. So let's just say, for the sake of this question, that west is positive. That doesn't really matter. You can say east is positive. All right. So if I do it this way, I'm going to just add all the displacement together. So I got a west of 45 kilometers plus, and then him going east here, so a negative 35 kilometers plus a 65 kilometer. Okay. So I'm adding them all together, but there's some negatives in there. So 45 minus a 35 plus a 65. The reason I made west positive because I want positive answers. In the end, I just knew there's more west. So we got 75 kilometers, which is positive, which means it's west. And then I'm going to take that and find the velocity. So the velocity is going to be my change in my position here, my displacement divided by my total time here. My head's getting in the way. There you go. My total time. So I got the 75 kilometers. What's my total time here? So I should probably do that. 0.95 plus 0.25 plus 0.85. So I got 2.05 hours. So 75 divided by this answer is 36.6 kilometers per hour. Because it ended up being positive, we were going west, right? Because it was positive, right? So there we go. Right? It's a positive number. If it was negative, it would be going the other direction. Yeah. There we go. I should probably put this down. Yeah, I don't want. You can find the total time by just adding them together. Okay. A car is moving. Well, they put some positive and negative, so that's good. Moving 18.2 meters per second is accelerated at a rate of 7.2 meters per second squared, so the units there are very important, to a new velocity of 40.4 meters per second. What's the time to require? Okay, so this is our typical accelerated motion kind of question. All right, so we got initial velocity, we got final velocity, acceleration, we got time, maybe displacement, depends on what they're asking. So remember, you only need 3 of these to solve these kind of questions when it comes to accelerated motion. So as long as I have 3, which I think I do, I have 18.2 for my initial, I have 40.4 for my final, I have an acceleration for my acceleration there, and we're looking for time.
Pardon the interruption.
Yeah.
Can Charles LaGrama please come to the front office? Charles LaGrama to the front office, please. Thank you.
Okay, so we want to find time. So we just have to look at the formula sheet that's above my head here and just find, maybe not that formula right there, but somewhere way up there somewhere, we want to find the formula without a d in it. So the formula that doesn't have a d in it is our delta v over t formula, just our typical acceleration formula. So remember that this stands for final minus initial, right? And then we want to solve for time. So we're going to times the time up to the other side, and we're going to divide by a. Remember, that's our steps there. You don't have to show those steps. It's also just multiple choice, but it'd be nice to remember what we're doing. So we're going to times that up to that side, and then we're going to divide by a. Divide by a. So we get the t there by itself. Okay, so once we got all that in there, we put our final 40.4 minus 18.2 divided by our acceleration. Sweet. And there you go. Just make sure that when you're dividing these numbers here, because there's a plus on the top there, you either find the answer, hit enter first, and then divide by the number, or put brackets around the top there. But we get, if you didn't do that, then you probably wouldn't get the right answer at all, or anything close to these other answers. But we get 3.08 seconds. There we go. Cool. All right. A car is traveling due north, then due west. From down to, what's the magnitude of the displacement? So this is one where we're going to have to deal with angles. So we got this car that's traveling due north. So I'm just going to draw a little picture out. So this is my origin. All right, and then he's going to go, it's going to go that way. He's going to go straight north, 12 kilometers. And then you're going to go west, never eat shredded wheat. So it's going to go this way, about 8 kilometers. And if we were going to do the long way, we'd find the x and y's, we'd add all the x and y's together, draw it. But this is honestly a nice, easy picture. We're just looking for this displacement here. Displacement, not distance traveled, so we're not going to add the numbers together, all right? And we're just looking for this hypotenuse here. Because north and west are 90 degrees to each other, we just use Pythagorean theorem. You have 14.4. Actually, let me write that down. 8 squared plus 12 squared equal to c squared. Doesn't really matter. C is equal to 14.4 kilometers. There we go. Cool. If you want to find the angle, you can find the angle. Look like they're just looking for the magnitude. So that's not the angle there. Okay. Which variable is constant for an object moving down an incline? It's constant for an object moving down an inclined plane. Acceleration. All right. Position's going to change because they're moving downwards. That makes sense. The velocity could be changing. It might be constant. We don't know. It doesn't specify in the question that it's moving down an inclined plane with a uniform motion. So we don't know if the acceleration is 0, but it could be. But it could be. I don't know. It's constant. Like this is like a for certain thing. So I'm going to say no. We don't know what the acceleration is. Is it 0? Is it not? I don't know. Time is always flowing, so I don't know why that would be constant. The position's changing unless you're standing still. It says it's moving, but is its velocity 0? Question mark? I don't know. But the only thing that we know, like this is not necessarily true, but for our purposes, acceleration is probably going to be constant. Whatever number happens to be, it could be 0. It could be, because 0 just means it would be moving, but a nice constant rate, or it could be accelerating. Right. Big space there for some reason. Let's give a moving theory. All right, truck is traveling, then accelerates for this distance. The speed of the truck will be, what's the final speed? Will then be, okay, so we're looking for the final speed. We have the initial speed, 14 meters per second. We have the displacement or position. They don't mention anything. These are all positive numbers. So let's imagine positives forwards or something. So everything's forwards here. It'd be nice if they give us a little bit more information like direction. And they give us an acceleration. Doesn't say it's slowing down like a negative acceleration or the acceleration is in opposite direction. We just want to find a good formula here. So this would be Vf squared is equal to Vi squared plus 2AD. Okay, so you don't have to rearrange this one. You just want to just take the square root of all of these numbers. All right, so square root of, I'm going to sneeze. Assuming that my units are good, we're all meters per second, so we're good there. So we have 14 squared plus 2 times 2 times 150. So you already see that I made a mistake over here. Let me just kind of correct that. So I figure out why this is also at 2 meters per second, but that's the wrong spot there. This is 150. Okay, plug all that in. Okay, that worked. 2 times 2 times 150. Make sure to take that square root. Oh, that first answer is if I forget to take the square root. So let's cross that one off. Seems a bit unreasonable, right? Think about these numbers, right? It's bigger than 300 meters per second. This is like faster than the speed of sound. It doesn't seem reasonable for a truck. But it's 28.82. There you go. 28.213 meters per second. There. All right. At an altitude of 300 meters, a water bomber drops a load of fire repellent. If the bomber is flying at a velocity, what's the horizontal distance? Okay, so it's going along. I'm assuming the altitude stays the same and it drops. So we've got some keywords here. But this is going to be a, here, I'm going to maybe draw a little picture of my plane here. Okay, so it's going to drop some water, and the water is going to fall and splash here on the ground, right? So it's not being like thrown up, it's not going to be thrown down, it's just going to drop, but it's moving sideways, so it's got that sideways kind of momentum, but sideways velocity that doesn't change. So it's a two-dimensional question, so it's going to be a T-chart where we deal with our X's and our Y's. Remember, so we got our horizontal side, we got our vertical side here, and then we just kind of fill in the information. Remember, in horizontally, it doesn't say in here, but let's assume that we're ignoring air resistance, right? That if it's moving horizontally, there's nothing, no forces there, it's going to move at a nice constant speed. So at the nice constant speed, I'm going to be just moving at 60 meters per second. This is my horizontal speed. It's not a dive bomber. It says traveling at horizontal. Well, it doesn't say it's traveling horizontally, but it's a nice altitude. And because it's not accelerating, the only formula I'm allowed to use is V is equal to D over T, right? That's the only thing I'm allowed to use in this formula, or this side, because there's no acceleration. If you want to, you can use the other formulas, just put A is equal to 0, but it just becomes this formula. Okay, and then we're looking for this D, right? That's what we're looking for, D, question mark, which is going to be V times T, after we figure out what the V, or what the T is. So to find the T, we're going to have to go to this side over here, find out what that T is. So I can use that on the other side. So let's go through. So we got the drops. So it's dropped, so that means it's VI is equal to 0. We know the altitude, so D is equal to, and if you want to, you can put the negative, but you could also just say down is positive. So if up here, if I say down is positive, this is going down 300 meters. So that's going to be a positive number. And then acceleration due to gravity, so down is 9.81 meters per second squared. There's nothing moving up here. Because nothing's moving up, what's the point of making up positive, right? Let's just make down positive. Try to find time. So I can use this formula here. VIT plus 1/2 AT squared. So now, remember in this formula, I was like, oh, we're trying to find time. Oh no, we're trying to find time, but time is in 2 spots. But what's nice about this, if V is equal to 0, 0 times anything makes this whole term, the whole first term, 0. Doesn't matter what the time is, it's just going to be 0. That's a nice mathematical simplification there. And now I can solve for time. Time's only in 1 spot. We can just rearrange this to solve for time. Okay. Let me just put that over here. So solve for time. We're going to times by 2. Okay. Get rid of the half. Divide by A. All right, let's divide by A. Get rid of the A. Take the square root. Get the time by itself. Okay, so now once I got all that in there, I could put all the numbers in here. So 2 times 300 divided by 9.81, making sure to take the square root. It's going to take 7.82 seconds to hit the ground. Okay, so then we take that time, we go back over here. Nope. Take this time over here, so we put that time in this spot over here. So 7.82 seconds. All right, that's from the previous part of this question, and then I could just jam those two numbers together there. So times it by 60. So 469 meters. There we go. Cool. Keep on going. We're in question 10. We're 7th way through. That's not too bad. Okay, so we got this graph. It is a distance time graph. What is the change in a distance or position, or distance here, between 2 and 14 seconds? Let's see. So the graph is not exactly what it should be here. So this dot right here. So we should set approximate because these dots are not exactly at 20 and 50. But it's close enough, all right? None of these questions here are anywhere close to what it could be if I was using exact decimals here. But we got 20 as my final, or my initial, 50 as my final. So if I want to find delta, which is change in, so it'd be final minus initial, then I can say my final is 50. My initial is 20. So my change is 30. It'd be nice if there was direction here. That's fine. Next two questions. Okay, so what is the change in time over change in, or change in distance over change in time, which is the speed. That would be better. What's the speed of this graph, which is just going to be the slope of this graph, right? So slope. I don't know if there's any better points here to use. So you could do the slope with using the 2 points that we have, which is hopefully going to give us a nice answer. It's going to have, we have our displacement from before, and that was over 12 seconds, right? So 14 minus 2. So 30 divided by 12, 2.5. Cool. Now I just want to know if there's a better answer. Because that 2.6 there could be better. I'm just saying if we use those 2 points there, 10 divided by 4. No, I still got 10.5. Okay, so 2.5 is pretty good. Yep. Let me write that down in this box here. Okay, so in the experiment, students observed, I'm just going to move this down here. The motion of a car moving with uniform motion. She made some measurements of the car's position over 5-second intervals. Which chart shows how to classify the manipulated, responding, and controlled variables? So she didn't make a measurement. She didn't measure the speed. So it's moving with the uniform motion, so they controlled that, right? So they controlled the speed. So I like these two because they're controlling the speed, right? That's good, that's good. Maybe I'll use the highlighter for this one. This is good. All right, that's good, that's good. But I don't like these ones over here. Okay. She made measurements. So she was measuring. She made measurements of the position, right? So that was responding, right? She was responding. And time usually is going to be on the x-axis, right? It didn't say that at certain distances she recorded the time. That would be the other way around. So time must be manipulated then. Right. 5 centimeters. There's time there, so I like A. A is a good answer for this one. The machine gun. Hey, I remember this question. I think we did this question, did I? That's weird. Why is this? I don't know where this question came from. That's weird. Okay, so the machine gun was invented in 1884 by this guy. The modern machine gun, like the M2, fires about 450 rounds per minute at a velocity of 860 meters per second. How far will one of these bullets travel? Ignoring air. Oh, it even says that. Ignore air resistance. That's good. If fired from an angle of 10.5 degrees. Okay, so this is going to be one of those T-chart questions again. So we're looking for our range. So I'm just going to draw out a T-chart here. Nice and big t-chart. Right, we're going to use lots of space, maybe even bigger than that. Also, I should probably leave a space for my vector diagram. So here's my vector, 860 meters per second at 10.5 degrees. Okay, that's good. And then and then we got the X, the horizontal direction, and then we got the Y, the vertical direction. Okay, so we got the horizontal, vertical here. So we could do what we did with that water bomber one. We could say, okay, so this is fired upwards. So let's just say up is positive. So since acceleration is down in this direction, so it's going to be negative 9.81 meters per second squared. I'm trying to find time, so I can use the time to find, because there's going to be v times t here. So remember, that's the only formula that I have to use here, because there's no acceleration. We have the v, we have the vi here. The vi is just part of this triangle, right? So if I go over to this triangle, and I draw the components, the x and the y components, of this velocity. This 860 doesn't belong in this chart, so remember that. So remember, to figure out what the velocities are for the chart, we have to determine the components. So I have to go sine 10.5 times my hypotenuse. So I get a y value. Okay, so I get a y value, 156.722. We put a bunch of decimals there, more than I need for the sig digs. Okay, so 860 times cos to find the x, right? So remember that we use cos for that one, we use sine for that one there. 845.59922. Okay. So now that we've found that, we just have to know one more piece of information on the vertical side so we can solve the vertical side to get the time, and then we can use the time on the other side here. Okay, so to get the other piece of information here, assuming that we have to make some assumptions, assuming it comes back down to the ground, if it does, then we could say our VF is negative 156.7225 meters per second, or we could say our D is equal to 0. All right, I'm just going to put a little star there. Assuming comes back down. There we go. So we have to assume it has to come back down. If it doesn't come back down, then we're into a big problem. So now, out of those, we have lots of different choices here, but because I have the VI and VF, and I'm looking for the T, I'm probably going to want to use this delta V over delta T formula. Solve for time, so that's delta V over A, but remember that's final minus initial. Final minus initial over A. Okay, let me just do this math again. 860 times sine 10.5. Okay. So I get 31 seconds, 9.915, something, etc. seconds. Okay, so now we're going to use that time. We're going to go back over here with the 31 seconds, put it in here. So we had to find that time on the other side. Seconds there. And we got this velocity here. V times t. And we get 27,000, right? So we get 27,018 meters. So remember that, because 1,000 is a kilometer. So this is 27 kilometers. So it looks like C there. Should give you more space for that one. Actually, I should give you more space for all these because you probably got the more condensed version. Okay. We got a book pushed at a nice constant velocity. Huh, weird. Okay. So we got this book pushed at a nice constant velocity. It requires a nice applied force. Now here's the key. Okay, so we got a nice constant velocity. If I say I'm moving at a nice constant velocity and then I say, hey, what's your acceleration? Because of this, my acceleration is 0. Nice constant velocity. And if I said my acceleration is 0, what's my F net? Which is mass times acceleration, which is going to be 0. Oh, there you go. Answer 0. Now, if it asks you what the applied force was, I don't know. I don't know what the friction is. It's just going to balance out because everything's going to add up to 0. Okay. So, next one. We have a tennis ball thrown from the ground with a velocity v0 directed 30 degrees above the horizontal. If it takes 1 second to reach the top, what was the magnitude of the initial velocity? I should give you more space for this one too. So they're looking for, like if I were to look at this T chart up here, we're looking for that hypotenuse of that vector. So that's what we're looking for. We're looking for what is that? All right. So to find the hypotenuse, I need to either know what the x is or what the y is. I know the angle, so that's good. They told us that it was 30 degrees. So let's put that in there. So if I can find the x or the y, then I found that question mark. So now what I got to do is I have to go to my charts, my T chart here. I hope that works behind my head there. We got the x. I don't think I could do too much in the x because they don't give me enough information about the x. That's my horizontal side. And then we have the vertical side, which is I think where this most of the information is going to be. So it says here that the ball takes a certain amount of time to get to its max height. Okay, so max height was 1 second. Okay, that means its final velocity, because the max height was 0. Our acceleration, which is down, let's say up is positive here. So down is negative 9.81 meters per second squared. Now, the reason the final velocity is 0 because it reached a maximum height, right? Where did I say that? It's top of its trajectory, max height. Right? It doesn't actually say max height, but that means max height. So that's why we're saying VF is equal to 0 here. Right? And then we're just looking for VI. Because if I know VI, that's the same as the Y value over there. So we just have to find a formula that involves this. Let's see. I think it's going to be A is equal to delta V over delta T, which is final minus initial. And my final is 0. Okay, so that part's 0. So if I want to cross something off here, because I always like doing that, cross off the zeros, makes my formula just a nice little bit easier here. Negative VI over delta T. And we're just looking for VI, so negative VI is equal to A delta T, and then I can move my negative over to the other side. Cool. All right. Yeah, we got negative 9.81 times the time. So my initial velocity is just 9.81. Okay, now that we know our initial velocity, we're going to take that, because that's not the answer. All right, this is just the y component of my triangle. So now what I'm going to do is I'm going to take my y component of my triangle, find the hypotenuse. I'm looking for the hypotenuse. So I'm going to cross up the 9.81 answer. Doesn't make any sense. A doesn't make any sense because the hypotenuse is always longer than the sides. So it's got to be one of the other two. And it's probably going to be the 19.6. Let me just see. So we got the sine 30 We know the opposite. And we're trying to find the hypotenuse. All right, that's what we're trying to find. So I'll do a little swap here. And we get 19.6 meters per second. There you go. Perfect. Okay, so we're going to use this graph here to answer this question. What's the total displacement of this graph? Well, it's kind of annoying. The graph is kind of, it's annoying because the graph is a weird shape. Right? But that's fine. How we're going to solve for the displacement of a velocity time graph. Remember, displacement is area. Of a velocity time graph, right? So once we have this velocity time graph, let me just write that down, because not everyone's going to watch this video. Okay, velocity time graph. Displacement is area. So we're just going to cut this up into areas. That's doesn't seem too bad. So we just take out our marker here. We just find these little individual areas here. Everything down or up to the x-axis. So if this was below the x-axis, it would be negative. Because this is above the x-axis, all these numbers are positive. And I hope that's all these numbers here are nice and easy to calculate. Plus, also, it might be nicer if I can draw a shape. Draw a rectangle. Let's go back down there. Oh, my computer's slowing down here. So I might have to split this into 2 videos here. How far are we along? All right, so, well, that didn't help. So let's put my marker here. Okay, so we have the bigger shape right there. It goes all the way across there. Then we have this triangle, and then we have that triangle there. So we have lots of different shapes to calculate here. There's nothing weird with the units, like the sides of meter per second, time. It's not like milliseconds or times 10 to something. So what you see is what you get. So the first little shapes here, so these are all just going to be areas, right? So this first one here is going to be 1/2 base times height, right? These ones here are just going to be length times width, right? So you're just going to add all of them together. So it's going to take me a little bit of time. So you can listen to me blubbers. I'm doing that first section there. 1 times 20 divided by that, so that's 10. So write these out. So first section, 10 plus second section right there. 1, 2, 3 times 20, 60. Plus the 3 times 10, so it's not as tall, divided by 2, so that's a 15. That's what I do next there. Then I'm going to do this one here, is a big 4. 1, 2, 3, 4, 5. Yep. 5 times 3 is 150. And then I'll do this one here, so that's 2 times 40 divided by 2. Yes, 40 again. Then I'll do that one there. That's 2 times 40. That's 80. I guess a lot of these I could have done in my head. This one here, that's 7. I'll do that 7. So base 1 times 4d divided by 2. That's 20. Hope we can get all these right. And the last one here, 2 times 30 divided by 2, so 30. Okay, and then we add them all together. Hope we got them all. 405. So it looks like 8. Yeah. So velocity time graph, area. The slope of a velocity time graph is our acceleration. Maybe that's the next question. Who knows? It's not. Okay. So we got some ticker tape here. We didn't do ticker tapes, but how a ticker tape works, you kind of read through the explanation here. It makes little ticks every so often. So in this case, the vibration of this is 50 hertz, which is 50 strikes per second. So that means if I saw 50 strikes, that would be 1 second. So right now I only see 5 strikes. So this is not a full second. And to figure out how much time is between each one of these, I can find like the period. Remember, period is equal to 1 over frequency. So I got 1 over 50 hertz, which is, if I do this, 0.02 seconds. So that's the distance between two of these dots. So from here to here, that's a t. But I'm looking from here all the way over to here. So that's 2 of these. So that's 0.4. So I have to look through all these numbers here and try to figure out which one's 0.4. I think this one here is 0.04, sorry. So the time is 2 of these, 2 times 0.02 seconds. I don't know why they use fractions for this answer. But yeah, it's going to be 0.04 seconds. There you go. Okay. A horizontal force of 15 newtons is applied to a box on a level surface. Its coefficients. What's the acceleration? Because then maybe you can use this for something else. It's sitting on a level block. You apply a force to it. Then its coefficient of friction is probably going to change. So this is kind of, I'm thinking it's going to remain stationary. The box does not accelerate. But the problem is those two things mean the same thing. I don't know if I like this question, but I'm going to answer it, I think, the way they want me to answer it. So I'm going to draw a free body diagram. A nice level surface. We got gravity, which is easy to calculate. Mass times gravity. Now, there's a reason we want that, right? Because if we're on a level surface, the force due to gravity and the normal force will end up being the same thing because they got to add up to 0, right? So that's going to be the same as gravity. I'm going to write that down some other different way in a second. They're going to apply a force here of 15 newtons. And then here I got a force backwards. Don't know how big it is, a force of friction. Okay, so to find acceleration, we need to find our F net, and we're going to divide it by my mass. Okay? To find my F net, I need to add all the forces that don't cancel out. Usually the forces in the direction of motion. So we got, I need a sign convention. So that was positive there. So we got the 15 newtons. We have the force of friction, which I don't know yet. Good, divide by mass. To find the force of friction, let's just do that on a different line here. We go mu Fn. So they gave us a mu, 0.30. It's that coefficient up there. But what's Fn? Well, Fn, because we're a nice level surface, is the same thing as Fg. So now remember the formula, which is not on our, you can't see here, it's up there, right? Has all these absolute values on it. They're not too concerned about direction. So even though gravity and the normal force in opposite directions, I'm not concerned about that when it comes to the mathy part here. So mu, 0.3, times my Fg essentially, is going to be 11. Now, the object is going to accelerate, right? Because they bypass that static friction, it's going to accelerate. Now, because they bypass the static friction, the coefficient of kinetic friction should be lower, so it should decrease. But maybe this is the instantaneous acceleration. Maybe. Okay, so now we know our FF. So that's 115, or 15, minus, so again, that's key because it's a negative number, because it's backwards, divided by my mass. I think that was 4 kilograms. Let me just double check. Yeah, 4 kilograms. All right, so 15 minus this answer that we just got, divided by 4. That gives us 0.807 meters per second squared. So it's not going to remain stationary, right? Because if the static friction force, remember that is always like if it's talking about static, that's the maximum it could be. It doesn't mean that's what it is. It's just what it can get up to, right? If I push with 15 and it doesn't move, that means there's 15 pushing back on me, right? It doesn't mean that there's more than that. So if I push with 10, even though the max is 11, what pushes back is only 10, right? So keep that in mind. What is the force of static friction? Okay, so I like this one. These are very typical inclined plane questions. So I'm going to draw this exaggerated inclined plane here, inclined plane of 25 degrees. I'm going to draw a box here. And, well, of course, I'm going to just label off some things like it is static. It's not moving, right? So I guess I didn't have to reiterate that twice in that question. There's nothing pushing on it, right? The only thing pushing it down is gravity, and what's holding it up is friction. So here I got my normal force. Remember, the normal force is always perpendicular to the surface. We got gravity here, but not all the gravity is pulling you down the hill, right? Some of the gravity is pushing you into the ground, and the ground pushes back. So that y component there. So remember how this one, you have to kind of shift your axis so that the x and the y are no longer horizontal vertical. The x and y are perpendicular and parallel to the surface that you're on. So like these are my x and y axis here. Okay, so because we're stationary, we can write a few things. Our a is equal to 0. Our F net, which is mass times the acceleration, is equal to 0. That means all of the forces in the x direction have to add to 0, and everything in the y direction has to add to 0. Now, we're only concerned about what's in the x direction because the x direction is where the force of friction is. So that's the one I'm caring about right now, the x direction one. Okay, so everything in the x direction has got to add up to 0. So what's in the x direction? Well, we have the force of friction. That's what we're trying to find. And the force of gravity, but not all of gravity, right? Just this x piece of gravity. The y piece, that deals with the normal force. I'm not worried about that. So if I want to find out what the force of friction is just like the negative value of whatever the force of gravity in the x direction happens to be. Well, how do I find that out? Well, we got to look at this picture here. Let's see, we got 25 here. All right, got 25 degrees. That's the opposite of this angle. So that's like the sine value. So it's FG sine 25 degrees. Okay, so sine, or sorry, so FG is just mass times gravity. So we got the mass. I could just write that out. Mass times gravity times sine 25. I don't have to write it out. I just punch in my calculator. So what's the mass of this thing? 25 kilograms. So we have 25 times 9.81 times sine 25. Always, like, hopefully by this point we're in the right mode in our calculator. We get 100. I should put a negative in front of that. We get 104. I'm just going to write down the whole thing. 103.647 newtons. So we just need 2 sig dig. So it's in the hundreds. The 3 doesn't round up. So it's going to be B. Okay, I'm going to do one more question. I'm going to finish off the rest of these tomorrow. All right? So I know there's a lot more questions here. There's like over 50 more questions, but hopefully this will be good for now. All right? A submarine here, submersible camera, is sinking at a constant speed. What's the upward force on this? Okay, so it's moving down at a constant speed. So the upward force would be like the buoyancy force. So here's my camera. It's sinking downwards, a nice constant speed. But what's causing it to go down is gravity. Even if it's in water, there's gravity, right? Yeah. And then why is it going at a constant speed? It's because my A is equal to 0. It means my F net, mass times acceleration, is equal to 0. That means all the forces, the sum of all the forces here, had to add up to 0. So that means there must be another force activated upwards here. Let's call that the buoyancy force. Let's go FB there. Those two forces have to add up to 0 according to this. So my FG is the same thing as my FB, but in opposite direction, right? So FB that we're trying to find, so go to the negative FG. We're just looking for the magnitude here, I think. We could say up is positive, whatever. So mass times gravity. So what's the mass of the submersible? 25 kilograms again. Genius. It's a big hammer. 245 newtons. Up. Cool. And there we go. So that would be D. Oh, that's it. Maybe D. There we go. Okay, so I'm going to stop there. And I will see you in the next video. Bye.